Hello, I'm Brian Wetton. I'm one of the large class instructors for Math 100 Flavor C in the 2013 academic year. I'm just making this short video with an introduction to Lagrange multipliers, which is a technique that can be used to solve optimization problems for functions of more than one variable. Two variables is what we'll consider, where the function values are constrained to be on a lower dimensional set. This is new material for Math 100 students. You are not responsible for it for the Flavor C final exam, but it is material that economics students will need in their later courses. So I've decided to make this introductory video to help you out. If you look online, there's lots of resources to help you get up to speed with Lagrange multipliers when the time comes, including the CLP textbook that you've used for Math 100 is number 1 in the series, and number 3 has a bunch of multivariable calculus stuff with a discussion of Lagrange multipliers. But this lecture should be enough to get you up to speed with the idea, enough that you can follow what's going on with your later economics computations. Okay, without further ado, let me switch to a little bit of a tablet view. And write out what we're going to do. All right, so I can here we go. Get my blue pen out and say that we're going to talk about Lagrange multipliers. And I'm going to start with an example that you're quite familiar with. Okay, it's the farmer field example. The first example that we did for optimization of functions of one variable. So remember how this went, right? There was an existing wall. And the farmer has 100 meters of fencing. And they want to make a rectangular enclosure with their 100 meters of fencing against this existing wall with this shape. So there'll be two sides like X and a parallel side of Y. And of course, now we can talk about functions of two variables. The area, right, of that enclosure is X times Y. We avoided really thinking of it this way when we first introduced it, because we didn't really have functions of two variables as our friends, but we're fine with it now. And then, of course, there's a constraint. You can't just take any values of X and Y. You have to take ones where 2X plus Y is equal to 100. Okay, and let's see how we went about solving this last time. Okay, so well, okay, we weren't comfortable with functions of two variables, so we eliminated the constraint and ended up with a function of one variable. So we said, okay, well, let's eliminate Y. So now we can have a function, area function of X, where all the Y's are replaced by this relationship with X. So it's X times 100 minus 2x. That's 100x minus 2x squared. We know that x has to be in the interval 0 to 50. Got to have something. And the two extremes, right, 0 and 50, give you no enclosed area. So you know the maximum must occur at a critical point. So we calculate the derivative. We set it equal to 0. And that tells us that x is 25. Right? And then we can go back and go, if x is 25, y is 50. Right? And then we can say that the maximum area is 25 times 50, which is 1250 square meters. You could even put units in it, okay? Okay, well, let's leave the beginning of the course, this easy description, and let's think of this as a function of x and y, and this is a constraint. Okay, and then we'd end up with something that looks like this picture. Okay, I have a function of x and y. Right, I can draw the contours. Right, those are values or curves where x times y is constant. Those are hyperbolas, right? If x times y is a constant, then y is that constant divided by x. So I get a bunch of curves, like these red curves, with increasing area. With increasing area, right, as I go this way and I follow those curves, right? And of course, in this problem, right, there is no maximum area because I can just have a bigger and bigger area, right, as I go farther and farther out. But there's the extra thing, which is the constraint. So you're forced to be on this line, right? In fact, we could have considered this as, you have at least 100 meters of fencing. So 2x plus y could be less than or equal to 100, in which case you would be considering, the problem on this triangle. And you would look for critical points in the interior of the triangle, and then you would try these three sides. But we certainly have intuition that if you use less than your 100 meters of fencing, you're not going to get the maximum area. So you really were constrained on this line. So let's start with that. Okay, and I'm going to show you the method of Lagrange multipliers for these kind of problems without much motivation. Okay, so this is a kind of a memorize me formula. And then I'll go back to this picture at the end, and I'll just give you an idea of where those things come from. Okay, so let's look at the method of Lagrange multipliers. For the farmer problem. Well, okay, before I put in the farmer problem, I can also give you a little bit of kind of abstract thinking. So here where we have our function of x and y that we want to maximize. That's this little f. It's x times y in this particular case. Right, and then there's the constraint that you can't look at any x and y in this plane, right? You have to look at x and y that are on that line. right? And I want to write that in terms of g of x and y is equal to 0. Well, I've got my 2x plus y is equal to 100. So I can easily write that as g of x and y being 0 will be 2x plus y minus 100. Okay, now up above, right, we had a function of two variables. We eliminated one of them. We got a function of one variable. We used Math 100, middle of Math 100 optimization techniques. Now, what I'm going to do now is overkill for this problem, right? But this is an example. I'm going to turn this into a problem with three variables, okay? I know that seems a little counterintuitive, but bear with me. So I'm going to make a capital F, which is going to depend on x and y and the Greek letter lambda. You can use L if you really don't like Greek letters, right? So I'm going to have a function of three variables now, right? And I'll show you the details for this particular example. But in general, it's always the function you want to optimize plus lambda times the constraint. Okay, and the constraint is always written as g of x and y is equal to 0. Well, I have a function of three variables. I want to optimize this. Right, and so I want to find critical points. But it's a function of three variables, so it's not just the partial derivative of capital X with respect to x has to be 0. And the partial derivative of capital X with respect to y is 0. But I also want the partial derivative with respect to lambda. I also want that to be 0. Okay, and you can make this plus, but now I've just realized there's something that's a little bit nicer if I make it minus. Okay, and don't worry if you've seen it as plus in other places, like I just wrote down, you can see right away that you're just changing the sign of this multiplier. And maybe I should tell you, this is the Lagrange multiplier. And it has a geometric meaning and an application meaning, and I'll show both of those in some detail later on in this lecture. Okay, well, let's think about this, right? Now I've got this capital F, which has got my things together, right? And I can remember the method of Lagrange multipliers as just construct this thing, find critical points. But it's a little bit more instructive to look at what comes out, right? So if I take the partial derivative with respect to x, I get the partial derivative of little f minus lambda, the partial derivative of the constraint. I get the partial derivative with y of little f minus lambda times the partial derivative with respect to y of the constraint. And then when I take the partial derivative with respect to lambda, remember x and y are constant, I just get g of x and y is 0. So this is the constraint. And that's good, right? Whatever comes out of this thing is going to be a point that's on the constraint, which it has to be, right? That's part of the problem. Right, and I'm going to find an even new color. Yeah, I don't know what color this is. Ooh, gray. Okay, I don't like gray much, but that's what we got. Now, you can remember the method of Lagrange multipliers from that formula in the blue box. Or you can remember it from this next stage in this gray box. And it's this formulation that has the actual meaning behind the method behind it. I mean, this is just one formula to remember, and take partial derivatives and find critical points. Or, as I say, you can just say, I'm going to start with this form, and I have three equations for three unknowns. I'm looking for xy points and values of lambda. Okay, well, let's see how that works out for our particular problem. Right, remember, I've got f of x and y is x times y. And g of x and y is 2x plus y minus 100. Okay, and so I'm going to use this form. I'm going to take the partial derivative with respect to x, I'll get y. And over here, I'll get lambda times the partial derivative of this with respect to x, which gives me a factor of 2. Right, and then I have the partial derivative with respect to y gives me an x. And then the partial derivative with respect to y gives me a lambda times 1. Right, and then I also have 2x plus y is equal to 100. Right, I'm on my constraint. Now you can see this this works out pretty nicely. Right, I can just put those in there and solve for lambda, and I end up with 4 lambda is equal to 100. That tells me that lambda is 25. And once I found lambda, then I can figure out the x value is just lambda, and the y value is 2 times lambda. Of course, the same solution that we had before. Okay, so why would you use this seemingly more complicated technique in an example that has this easy formulation? Well, there's two reasons. Okay, this is just a warm-up. Okay, it's certainly easier to do this computation than it was to do the whole Lagrange multiplier thing. But remember, this computation relied on us being able to eliminate one of the variables from the constraint. And of course, that's not always possible to do for some curve that you could write down in space that is the constraining curve for where the function values are allowed to be considered. And you may not be able to find a way to eliminate one of the variables to get a function of one variable. And so this is a more general form. The other thing is this lambda has a meaning, and it comes up as being a kind of significant thing in economics problems. Okay, and I'm just going to show you what it ends up being in this particular case. So I'll say that lambda has meaning, and I'll show you. Okay, so we had with 100 meters of fencing, we had x is 25 and y was 50. What would happen if we had a little bit more fencing? And as usual, this h is going to be some small number. Now, you can redo the whole computation that we did before, but I think it's hopefully intuitive that this factor of 2 is a geometrical result, not a specific result for 100 meters of fencing. Right, and so if I go from 100 to 100 plus h meters of fencing, then I'm going to use a quarter of it for each of the two sides and half of it to make the parallel side longer. So x will go to 25 plus h over 4. Got two of those. And y will go to 50 plus h over 2. I got one of those. Right, so that's how I geometrically I'm going to use my extra fencing. I'm going to keep the same ratio. And again, you can start with this and do the whole computation again and see that this will come out with the same geometric factor. So that means if I have a little bit extra fencing, I'm going to get a little bit of extra area. Right? It'll be x times y, so it'll be 25 plus h over 4 times 50 plus h over 2. And remember, we're thinking of h as small. There's going to be a small term that I'm going to neglect coming up. Right? So I'm going to have my 1250, right? That's the that I got from 100 meters of fencing. And then I'm going to have an h term, which is going to be 50 divided by 4 plus 25 divided by 2, right? Which, funnily enough, is 25. And then I've got an h squared divided by 8 term. Well, I'm thinking of h as being small, and so this is a small correction, and this is negligible compared to that, right? So I'm going to go approximately equal to that for h small, which I said it was from the beginning. So now my area is 1250 plus 25 times h. Well, this is the value of lambda that we came up with. And so now we have the interpretation of what this Lagrange multiplier is. It's the ratio of changes to the optimum value to changes. Maybe I should put marginal changes in the constraint value. So you had x plus 2y was 100. Well, if you change that by h, right, then the optimal area that comes out changes by 25 times h. That's the meaning of this this lambda. Okay, and that's why I changed my plus here to the minus to get this form. Again, mathematically they're equivalent, but in this form, the sign of lambda is right to get this result. Okay, well, let's do one more. Again, it's going to be a little bit artificial because in this example, I could solve for the constraint and eliminate one of the variables, which of course you can't always do. And that's one of the real powers of Lagrange multipliers, in addition to this stuff here. Okay, and for this one, it's going to be one of our labor versus machines production functions. If you go back to one of the earlier lectures, we talked about this, right? So I'm going to have production is going to be a function of how much of company resources I put into labor and how much company resources I put into machinery. Its labor is used in economics terms, but usually the machines are called capital. Okay, but I've got M for machines. Okay, and this is the form of the model I'm going to take. So this is a scaled model of how production could depend on the amount of labor and the amount of machinery that you have. And of course, there's got to be some constraints. I'm saying that the total resources are scaled to be 1. You can divide them up between L and M, but you do have this constraint. You've only got so many resources you can throw at production. Okay, and now the question is, right, how do you divide up to maximize the production that you get? And you can see right away, right, you don't want to have no M or no L, because then you're not producing anything, right? It's got to be some mix that gives you the optimal production. And again, we could eliminate M and have Q as a function of L only and make some progress that way. But let's use the method of Lagrange multipliers. In fact, the algebra ends up being a little bit easier. And remember, the lambda value that comes out will be the ratio of increased production to increased resources. And so it's going to have an interesting meaning that you want to know. So let's write the constraint equals 0. And yet I'm going to use this form of the equations. So I'm going to have the derivatives, x and y, of the function I want to optimize are going to be lambda times the derivatives of the constraint. Okay, so let's do that and see what comes out. So I'm going to have dq dl will be lambda times dg by dl. dq dm will be lambda times dg by dm. And I'll have the constraint L plus M equals 1. Okay, well, if I take the derivative with respect to L of this one, I'm going to get 2/3 L to the minus 1/3 times M to the 1/3. And if I take the derivative of G with L, I just get 1. Right, okay, and I get a similar thing going on here, right? Here I get 1/3 M to the minus 2/3, and then I'll have L to the 2/3 here, and when I take the derivative with respect to M, I get 1. Okay, and again, the algebra comes out kind of nicely. I'm going to take this one, and I'm going to divide by that one, right? Oh, not lambda. These are lambdas. It's all right. These are lambdas. And I'm doing that to eliminate lambda. Okay, and so what happens is I get 1/3 divided by 2/3, that's a half. Get L to the 2/3 divided by L to the minus 1/3. Oh, that's kind of convenient. That's L. And then I get M to the minus 2/3 divided by M to the 1/3. That's M to the minus 1/2, or M to the minus 1. And the lambda divided by lambda is 1. That's why I did that. Okay, and so I get L is going to be 2 times M. But then if L plus M is 1, right, then I get 3M is equal to 1. That tells me that M is equal to 1/3 and L is equal to 2/3. Okay. So this is the division, right? More labor than machines in this particular model arrangement. And of course, if you wanted to figure out the lambda, you can just plug these numbers in to get the same value in both of those equations. Okay, so this is a recipe now I've described to you for Lagrange multipliers. I want to give a little bit of a theoretical description of where this comes from. And I won't show all of the details, right? But I'll give you at least a flavor for where this comes from, because otherwise it's just something I told you, write this down, write these equations down, and then do some algebra to solve them to find candidates for optimal points. Okay, well, you've got these three equations here. And this one's pretty obvious, right? You have a constraint in the problem. You have to satisfy the constraint, right? You're only allowed to operate under some relationship between x and y, and that's got to be satisfied. And then you're trying to find the optimal value of f that's on that curve. Right. Well, what do these two mean? Well, I have to appeal a little bit to an idea about vectors that you probably don't know yet, right? I want to look at a point, right? And I want to make a vector direction. So how do I make a vector direction? I have to tell you the x and y coordinates of an arrow. Right, and I've got two things that I want to look at. One is I've got this vector that's got an x component, the partial derivative with respect to x, and the partial derivative with respect to y. So that points in a certain direction. At every x, y point, you can compute these two things. They give numbers, and that gives you an arrow. Right? And this is called the gradient of f, this direction. Well, okay. And then on the other side here, I've got the same kind of thing multiplied by lambda, but with g's in it. So I've got dg dx, dg dy. That's the gradient of g. Okay, and these two relationships say, not that these two gradients are equal, right? They're not equal unless lambda happens to be 1, right? Which won't always happen. But they point in the same direction, right? This vector direction being a constant multiple of this vector direction means they're not the same value, but they point in the same direction. Or if lambda is negative, right, then they point in like the exact opposite direction, right? But if you think of a direction as being a line through this point, then you can say that they point in the same direction, even if lambda is negative, right? So these two equations tell you that the gradient of f is parallel to the gradient of g at optimal points. Okay, and now I can go back to my original picture for the farmer's field. And I can tell you that the gradient, right, the gradient is always pointing perpendicular. Gradient of g points perpendicular to the constraint. Right, and the gradient of f points perpendicularly, to the level lines of the function f. Okay, and so now you can see why that geometric condition comes up. Think about this, right? You're trying to find the biggest value of f that you can possibly find on this line. Now think of values of this function f, right? They're constant on these curves. Well, these are all small values, and you want to get the biggest value you possibly can. So you keep pushing these curves, you keep pushing them further and further until you just touch, and that's exactly where the gradient of f is pointed in the same direction as the gradient of g. Okay, so you didn't need to know that, right? To use this recipe to find optimal values and to calculate values of lambda that tell you something about how the optimal values will change as you change the constraint. But I just wanted to end with at least some idea of where these equations came from. Okay, and with that, I will end. Again, this is optional material. It is not testable. I'm only making this video for anyone who happens to be interested, but specifically for economics students who will be using these ideas in their later courses. Okay, good luck with this material, the final exam, and everything else you've got going on at the end of term.